Okay, our next lesson is on the concept of torque and rotational equilibrium. Now, torque is the rotational equivalent of force, and if you have a torque on an object, then it will spin. Let's consider just pushing on a door. We apply a force on the door a certain distance away from the hinges, and that creates torque. So torque, we use the Greek letter tau for that. And the amount of torque depends on the force and on the distance away from the pivot. Now, you only get torque if those are applied perpendicular to each other. The torque units then will be newtons of force times meters of distance to the pivot. Torque is in Newton meters. That's the first key fact. Now, torque, it turns out, it's actually a vector, and the directions of torque can be counterclockwise or clockwise. Now notice then that if a force is acting at the pivot point, that means no distance from the point of the rotation, then there's not going to be any torque. There's no rotational force, if you like. To find the net torque on an object, you're going to say take the counterclockwise and subtract the clockwise. And our symbol for that will be sum of the torques, or we could also write net torque. Let's consider a first example. So here's a seesaw, and we've got a couple of children on there. Let's start with a force diagram for the seesaw. So there's going to be a weight on this side. That's a 10g weight. This is a 5 kilogram child, so there's a 5g weight. And then there'll be a support here, a force pushing up at this pivot point. So this is 10 times 9.8, so that's 98 newtons of weight. Mg is 98 newtons. Over here, mg will be 49 newtons, and then there's an unknown normal force here. Okay, so we want to find the directions of torque. So in order to do that, you can imagine, say if you put your pencil on the page and hold it here at the pivot point, if you push down on this side, you're going to create a clockwise rotation. So clockwise, CW, that torque is due to the 5 kilogram child. Now we remember a torque is a force and a distance. The force is the gravitational force, 49 newtons, and the distance is 1.2 meters to the pivot point. And so that is 58.8 Newton meters of clockwise torque. Now the anti or counterclockwise torque comes from this 10 kilogram child, which tends to make the beam rotate in this direction. Once again, a torque is a force times a distance. The force is 98 newtons. That acts 2 meters away from the pivot. So we have 196 newton meters of torque. So the net torque, then you take the bigger one and subtract the smaller one. And what do we have there? We have 137.2 Newton meters of counterclockwise torque. Now the fact that the net torque is counterclockwise, that's going to imply a rotation that's counterclockwise. It's actually going to accelerate in the counterclockwise direction. Now, for a clockwise torque, that is going to give us a rotation that is clockwise. Now, if the object's not rotating at all, that tells us that the anti-clockwise and the clockwise have to be canceling each other out, or another way to put that is just that the net torque is actually 0. And this is the main problem of interest for us. Now, in the problem that we had previously, we had the pivot at the middle of the seesaw. If the pivot isn't at the middle, then we need to consider gravity. I suppose I should put that force on there. Do we have, oh, the seesaw, the 10 kilogram beam. Oh yes, that's important. Let's put that on there. My mistake. Yes, the beam itself has weight. But then notice that we that didn't affect our analysis because these two forces act at the pivot point and therefore produce no torque. Forces acting at the pivot, there's no distance there. So therefore, no torque. Okay, but if the pivot point were somewhere else, then we would need to consider the torque created by the gravitational force, by the weight of the object. Now, that at first glance may seem difficult because every little bit here has some weight, obviously, right? Every little chunk of the meter stick, and different weights are at different distances from the pivot point. But there's a simplifying concept, and that's known as the center of mass. The center of mass is the point where gravity acts on average, and it's just at the center of uniform objects. So it doesn't matter where you hold the object. On average, gravity acts at the middle, and the amount of torque that gravity exerts on this beam will be this force times the distance to the pivot. Okay? And this force is acting at this uniform at the center, provided this stick is uniform. Here's an example to illustrate that. So here we've got a beam, and obviously there's a 20 Newton weight there, and that's one force that acts on the beam. We'll draw the force diagram here. So 20 newtons of weight. Then there'll be an upwards force here at the pivot. But then, of course, there's going to be the weight of the beam itself acting in the middle of the beam. Here, let's fix these a little bit so that looks better. Okie doke, just like that. Okay, so now we want to find the net torque. So we first ask, okay, are there any clockwise torques? Sure, if this is the pivot point, oh my goodness, it's being very troublesome here, sorry. Okay, try that again. So if this is the pivot point, this weight here, the beam weight for the 8 kilogram object, and that's 78.4 newtons of weight, that weight right there is that force will cause the object to spin clockwise. So this torque is due to the weight of the beam. And again, if you have trouble seeing that, just put your pencil on top of the object, hold it here with your finger, and then push down at this point, and you'll see that your pen tends to rotate in a clockwise direction. Now, torque is a force times a distance, so we have to multiply this 78.4 newtons of weight by the distance to the pivot. Now, this is a 5-meter long beam, and gravity acts on average at the center, i.e., we know that the center of mass, this point right here, is 2.5 meters from the end. Well, we need to know the distance to the pivot point. By subtraction, we know that'll be 1.5 meters away. And so multiplying this force by this distance, we get 117.6, 117.6 Newton meters of clockwise torque. Now, this support force here acting at the pivot produces no torque, but there will be anti-clockwise torque due to the 20 Newton force. The amount of torque will be the product of force and distance to the pivot. 20 newtons acts 1 meter from the pivot, so that's 20 Newton meters of anti-clockwise torque. So the resulting torque then, just the difference of those two, is 97.6 Newton meters in a clockwise direction. So this is how we find the resultant or net torque on an object. But the problem that we're going to be interested in is the equilibrium problem. And an object in equilibrium doesn't rotate, therefore the torques are balanced. Or another way of putting that is just that the sum of the torques, which say is the anti-clockwise minus the clockwise, is 0. Now previously we had studied the equilibrium problem for a point object, and we said such a point object had no net force. So say in the y direction, that might be forces up minus forces down are 0, so that forces are balanced up and down. So for an extended object where rotation is a factor, we have a second condition now, In addition to balanced forces, we are also going to apply the balanced torque condition. And this just opens up a new range of interesting problems that we can look at. So here's an example. We'll probably demonstrate this in class. This is just a meter stick, and these are the centimeter markings on that meter stick. And we're just going to hang some lab weights from it and try and balance it out. So here's a 100-gram mass. Okay, so there'll be a weight here. Then the meter stick itself has weight, and that'll act on average at the center of mass, which is the 50 mark. There's an unknown weight out here at the end. That's what we're trying to find. And then we'll be holding this up with our fingers, so there'll be some upwards force here, like that. Now let's label these forces. So this one here is M1G, I guess. So that's 0.1 kilograms times 9.8 newtons per kilogram. So that's just 0.98 newtons of force downwards here. I guess we could just call this a normal force or a support force. This is the mass of the stick, and that's also, the weight of the stick, and that's also 0.98 newtons. And then this one is an unknown, and I'll just call that mg. Okay, so this stick is in rotational equilibrium. That means that the torques have to be balanced so that the anti-clockwise and the clockwise are canceling each other out. Now, holding it at the pivot point, clockwise torques comes from this unknown weight here. So the clockwise torque is due to the unknown weight. And we always go through this procedure, right, to make sure that we're identifying the correct force. Now, we know a torque is a force times a distance. The force is clearly the weight of the unknown mass. The distance will be how far does it act from the pivot. Well, these are centimeter markings, so this is 45 centimeters, or 0.45 meters. Okay, so that's the clockwise torque. These two act at the pivot and produce no torque. So there's no torque coming from these two, as we argued previously. Now, let's consider the clockwise torque. So clockwise torque comes from the 100-gram mass. And we know a torque is a force times a distance. The force we worked out was 0.98 newtons of weight. And the distance from 15 to 50, that's 35 centimeters, or 0.35 meters. So the fact that these torques have to equal each other gives us this condition right here. And this is going to enable us to solve for the mass m. So this is, let's see, 35 over 45 is 7 over 9 times 100 should be 77.7 grams, or 0.077 kilograms. So these are the sorts of problems that we're going to work on. This will be a typical sort of analysis. So we are going to draw the force diagram like we did in our unit on dynamics. And then instead of writing force equations, well, in addition to writing force equations, we're also going to write torque equations, remembering that a torque is a force times a distance. Now, up until now, every problem had a clearly defined pivot point. Let's look at a case where that isn't so. Say a person down in push-up position, so this is their hands and this is their feet. Well, you could imagine the pivot point being at their toes or at their hands, or perhaps at the center of mass. It could be at any other place as well. The good news is it doesn't really matter, because as long as the object is in equilibrium, any point can be used as the pivot point. So that's good news, and therefore it means that we should pick a convenient point for ourselves. Now, what is convenient? Well, we'll see that as we do a few more examples. But it turns out that you want to put it where you have an unknown. Let's see why that is. Okay, so here, let's analyze that problem. And here we have the person in push-up position. And so in push-up position, the forces on them will be their weight, mg, and we see that's given as 700 newtons. Then their floor is going to be pushing up on their toes. That's a normal force, if you like. of the ground underneath pushing up on the toes. And then this is another normal force, the ground pushing up on their hands. Okay. Now, this person, let's imagine that they've set, they're in like a plank, so they're not moving at all. That means that the torques have to be balanced. They're in rotational equilibrium. And if they're not moving up and down, they must also be in force or translational equilibrium. So what are we asked to do? Okay, we're asked to use the toes as a pivot point. And I sometimes will just draw like a little fulcrum here, just to communicate that that's the point that I've picked as the pivot point. Okay, so use the toes as a pivot and write a balanced torque equation. Okay, so balanced torques. Because this object is at rest, the torques have to be canceling each other out. Now, with this pivot point, the mg force tends to rotate it in a clockwise direction. So the clockwise torque is due to the weight force, mg. We remember that a torque is a force times a distance to a pivot. We have 700 newtons of weight, and the distance to this pivot point is 50 centimeters, or 0.5 meters. Now, anti-clockwise torque, it's a little harder to see this, so you put your pencil down here, you hold it at the pivot point. If you push up here, then there's going to be rotation in this direction. This is an anti-clockwise torque due to the force acting on the hands. Now, a torque is a force times a distance. The force is the unknown hand force. How far does that act from the pivot point? Well, you have to add 30 and 50 centimeters and say that this acts 80 centimeters, or 0.8 meters from the pivot point. So now, this statement of balanced torques becomes an equation that you can solve for the hand force. So let's see, that's 5/8 of 720. Sorry, my mental calculator is failing me. That is 437.5 newtons. Now, we're not finished with our analysis because we have another condition that we can use. You see, because this object is at rest, it's also in translational equilibrium, and that means the forces have to be balanced. So that means that forces up, balance forces down. Oh, there we go, it finally responded. And therefore, say, are you going to stop or not? There we go. Forces acting up have to equal forces acting down. Now, the forces acting up include the normal force on the hands and the normal force on the toes, and then the force acting down is the weight. So this we found was 437.5, and then this was the 700 newtons of weight. So we can find this unknown toe force now just by subtraction. So what is that? 262.5 newtons of force acting at the toes. So this is a very typical torque problem then. A very typical equilibrium problem. So we draw the force diagram, we apply the balanced torque condition, and we apply the balanced force condition. Now, remember we said that any point could be the pivot point, and you could imagine putting it at the hands. Now, if you put it at the hands, we know that the force acting at that point, because of zero distance, is not going to produce any torque. So that means that the hand force unknown is not going to appear in this equation. The only two torques are going to come from the toe force and from the weight. So about this pivot point, we could solve the previous problem in a different way. So with this pivot point, now mg is an anti-clockwise torque. And so you would have 700 newtons acting 0.3 meters from the hand pivot point. Now the clockwise torque comes to us from the toe force down here, which is acting 80 centimeters away from the hand pivot point. And if you solve this equation for toe force, you'll get exactly the same answer that we just got on the previous page. So this shows a couple of things. It shows that the pivot point can be anywhere, and it shows that we could have solved the problem using two torque equations instead of a torque and a force equation. So here's a problem we'll work on in class, and here's one for you to try now. So we've got a person here at the end of a diving board. And first of all, a conceptual question. What will the force diagram look like for the board? So we're drawing the forces acting on the board. There's some information here. The person has weight, the board has weight, and there's a couple of supports. And it's multiple choice, A, B, and C. Think about which one of those is right. Okay, so hopefully you've had a chance to think about that for a moment. And hopefully you realized that because the board has weight downwards, let's do nice arrows here. So the board's got weight, and the person's got weight. If we imagine, say, support number 1 is the pivot point, so then we can see that support number 2 must actually be pushing upwards in order to balance these two clockwise torques. If, on the other hand, we imagine support 2 is the pivot point, then support 1 has to be pulling down on the beam in order, again, to balance the torques. So the correct force diagram is actually answer choice, what is that? That's B. This is the correct force diagram. And you can try it. If you take out a ruler and try and make it into a diving board, you'll see that your finger at the end actually has to push down on the diving board, and this second support is pushing up. So now let's turn that into a numerical problem. Let's analyze it. Okay, well, first of all, this is tiresome. Pause this. Okay, so there's the force diagram. And so let's call this the force from support 1. Here's the force from support 2. This is 10 G's of weight, and this is 45 G's of weight. Now, we're told to use the first support as a pivot, so here I'll draw a little fulcrum here. This is going to be my pivot point. Remember, I can pick any point I like as the pivot point. Putting it here means that F1 won't appear in the torque equation. So let's write that balanced torque equation. Torques counterclockwise will equal torques clockwise. With this pivot point, both of these weights tend to rotate clockwise. But because each force acts at a different distance, we're going to have two torque terms here, one for each weight. Now, it's a 3.75 meter long board, so this force here acts at the halfway point. So that's 1.875 meters. So we've got 10 G's of weight acting halfway along the board. Then we've got 45 G's of weight, this one out here, acting at the end. That'll be the full 3.75 meters from the pivot point, which is here. Counterclockwise torque comes from this force here, F2. So due to the F2 force. And remember, a torque is a force times a distance. The force is the unknown F2. The distance to the pivot is given as 1 meter. So this statement of balanced torques becomes an equation that we can solve to find the force F2. Once we do that, we can say balanced vertical forces, so forces up have to equal forces down. The upwards force is just F2, and that has to be balanced by the 3 downwards ones. Although F1 didn't appear in the torque equation, because it's right at the pivot point that I picked, it does appear in the force equation. So forces up are F2 and forces down are F1, 10G, and 45G. And then we can solve this equation for F2, F1. Solve the torque equation for F2, put it in here, and then find the value of F1. Okay, and here are the values that we get for F2 and for F1. And this is a very typical problem for us. So once again, force diagram, balanced torque equation, and balanced force equation. And we'll pick up some more problems like this in class.